Wang Yang from here will tell us about computational power of SPT phases for integer spins. So please proceed.
I'm very sorry for the delay. The projector somehow does not work with my laptop. So today I'm going to talk about characterization of computational power in SPT phases in integer spin chains. This is a work which I have been working on with Robert and Anna. So
somehow it goes.
So this is an outline of my talk. First, I will give a very brief introduction of environment-based computation, which I will abbreviate as MBQC in this talk. And then I will move on to a discussion of 1D AKRT states and show that it can be used as MBQC resource state. And after that, I will discuss the string order parameter in the 1D SPT phases, which can be used as, which coincides with computational order parameter. And this part 3 will be the central part of my talk today. And finally, I will briefly discuss the generalizations to arbitrary integer spins beyond spin 1. So first, a very brief introduction of MBQC. MBQC starts with resource states, which are many-body entangled states. And by just doing single qubit measurements on these resource states, we can realize universal computations. The MBQC resource states, examples of the MBQC resource states include 2D cluster state and also 2D AKRT state. So this graph, this picture here shows how MBQC is processed by doing single qubit measurements. Basically, on each side in this picture, we have a qubit. The colored size represents the qubit that we are going to use in MBQC. And all of the other sides, these ones without colors, will not be used. Essentially, they are removed. And so measurements will be performed in different bases on these colored qubits. And the arrows here represent the direction, represents the coordinate axis in which the measurement is performed. And so here in this picture, each column represents a constant time slice. So in practice, let's say we measure the column within this left depth square, and we also measure all of the qubits within the column to the right of this, to the next to this red depth square. That's the right of it. And then essentially we evolve the system from the left red depth square to the right red depth square. And as you can see from this picture, each row corresponds to a qubit. Actually, that's a logical qubit. The qubits residing on each side are actually the physical qubits. And in this way, both local single qubit rotations and also SIM updates can be realized. And MBQC also has technological applications. For example, it has been applied in realizing quantum computation in photonic systems. And the usual model for quantum computation is the quantum circuit model. And they are equivalent but quite different. So quantum circuit model, in quantum circuit model, people start from a product state. But in MBQC, we start from a entangled state. And in quantum circuit model, the complexity of the system is built from unitary evolutions, including single qubit rotations and 2-qubit symmetry. But in MBQC, only single qubit measurements are performed. So there's basically no unitary evolution. And in the conventional quantum circuit model, the measurements are performed only at the end. But in MBQC, the measurement is performed at every time slice. And in particular, MBQC is destructive and irreversible because of the measurements. And so in the first 2 slides, I talked about MBQC in 2D. But now let's focus on a simpler situation. That is to say, the one-dimensional MBQC. And in 2D, we can use MBQC to realize universal computation. But in 1D, we can only realize single qubit rotations, not the signal phase. So that is to say, MBQC in 1D is not universal quantum computation. But still, 1D provides a good starting point to analyze more complicated situations in 2D or even 3D. Here are 2 examples of 1D MBQC resource state. The first one is the spin-1 half cluster state. And the other one is the one-dimensional spin-1 AQRT state, which will be the focus of my talk today. The Hamiltonian of the AQRT state is like this, in which this Si and Si plus 1 are spin-1 operators. And we have 2 terms. One is S of the form S dot S. The other one is S dot S squared. These 2 terms have a particular, the coefficients of these 2 terms have a particular ratio, which is equal to 1/3. And I will discuss in more detail later. The ground state of the 1D AQRT Hamiltonian can be written in this form. So basically, although we have spin-1 on each side, we split the spin-1 into 2 spin-1 halves. So after the splitting, we have 2 spin-1 half particles on each side. And this is generally called fractionalization. And but as we know, when we combine 2 spin-1 half particles together, we have not just triplet, but also singlet. So to impose the spin-1 condition, we also need to project out the singlet component, which is represented by this dashed ellipses for pairs of the spin-1 half particles. And the key feature of the AQRT state, or to say the ground state of the AQRT Hamiltonian, is that these spin-1 half fractionalized particles form pairs of singlets. But the 2 spin-1 half particles connected by this singlet line reside on 2 different sides. This is actually 2 adjacent sides. So this is actually a law. As I said, we need to project all the singlets on each side, but it is allowed to have singlet combinations with spin-1 half particles coming from 2 different sides. I will go back to this AQRT state in more detail later. And since I'm going to, so since the talk will be focusing on SPT MBQC, here I would like to very briefly introduce the concept of SPT phase. That is to say, the symmetry protected topological phase. This is a definition of the SPT phase. Basically, SPT phase is a gap phase which cannot be arithmetically connected to product space without gap closing by symmetry preserving local unitary transformations. The figure on the upper right page here shows an SPT phase and a trivial phase. It's a trivial gap phase here. And there will be, in general, will be a phase transition line separating these 2 phases. So for any state in the trivial gap phase, we can deform it into a product state without gap closing. But if we want to deform a state in SPT phase into either a trivial gap state or equivalently into a product state, we have to cross the phase transition line. And in general, there will be a gap closing along this phase transition line, which is in contradiction with the definition of the SPT phase. Okay, and there are quite many features of the SPT phase. These include, for example, short-range entanglements, fractionalization, edge states, and also in 1D, the non-zero string order parameters. These concepts can be intuitively visualized from the representation of the AFK chain that I described earlier. For example, we split every spin 1 side into 2 spin 1 half particles, and this is related to the concept of fractionalization. And as you can see, all of the spin 1 half particles in the AKRT state are connected by a symmetric line, except the spin on the left edge and also the spin on the right edge. And these are edge state spins, which is related to the edge states in the features of SPT phase that I described earlier. And actually, all of these concepts are intimately related. For example, it's clear from this picture that fractionalization leads to the formation of edge spin. But this fractionalization is also related to entanglement. So, so as you can see, when we split the spin 1 particle into 2 spin 1 halves and basically connect, for example, this red particle with this one by a single line, we actually entangle these 2 spin 1 half particles. So there's also entanglement coming from fractionalization. And entanglement is actually related to the fact that SPT state cannot be deformed to product state because there's basically no entanglement in product states. Okay, and okay, so and then as I talked about in the beginning, we have some MBQC resource states which are very good. For example, the cluster state and the AKRT state. But the point is that they are very rare in the Hilbert states. So the question is, can we expand the range of the states that can be used for MBQC purposes? And in 1D, this question is answered by a series of papers. So the discovery is that 1D SPT states can be used as MBQC resource states. And in this way, we have a notion of computational phase. For any system within this computational phase, we can realize the MBQC. Actually, in 1D, computational phase coincides with SPT phase. So this greatly expands the range of MBQC resource states. And this is an example. So in 1D, as I mentioned earlier, for a KRT chain, these 2 terms, so the ratio between the coefficients of these 2 terms within the Hamiltonian is fixed to be one-third in a KRT chain. But let's say we relax this constraint and we consider general coefficients for these two terms. And then we will get a phase diagram in terms of the parameter theta. AKRT lies somewhere in the first quadrant of this phase diagram. But the crucial thing is that there is actually an extended region within the phase diagram of Haldane phase, which is an SPT phase. Basically, this means that, as I described in the last page, any state within the Haldane phase can be deformed into a KRT state by symmetry preserving local unitary transformations. And according to the papers listed here, the systems within the Haldane phase can be used for MBQC in 1D. But then but then the question is, do the systems in the Haldane phase have the same computational power? And this question is answered by a recent unpublished work by Robert. And the finding is that there's actually a notion of computational order parameter nu, which can characterize the computational power. So what does this mean? This means that let's say we are given some computational task, and then you will find that basically the number of qubits to implement this computational task is proportional to 1 over mu, where mu is the computational order parameter. So this means that if mu is very small, for example 0, which means that then the number of qubits will diverge, and then that means basically there's no way to realize computation MBQC in this kind of system. But if mu is not equal to 0, then we can realize MBQC. But the number of qubits required for a given task will be dependent on the value of mu. And let's come back to the spin 1. That's called the bilinear biquadratic component, the one in the previous page, this one. Let's come back to this component. Then, as I said, within the Haldane phase, which is our SPT phase, we can realize MBQC. And so basically within the Haldane phase, we have a continuous spectrum of the computational order parameter nu. So it is equal to 1, reaching the largest value at the AKLT point. Away from the AKLT point, this computational order parameter nu does not vanish, but it's still non-zero. So basically in this Haldane phase, the value of nu varies continuously. Okay, and but before discussing SPT MBQC in spin 1 models, let me first discuss the conventional MBQC exactly at the AKLT point. So as I said, the AKLT component is defined in this way, in which the operator as are spin 1 operators. For example, in SZ eigenbasis, the operator SZ is a diagonal with elements 1, 0, -1. And SX is a symmetric off-diagonal matrix. But this form of the component is not very enlightening. A better way to write the component is like this. So basically, the AKLT component can be written into a sum of projectors. So let me explain a bit more on what this projector P2 means. Let's consider two adjacent sites, I and I plus 1. And according to the momentum addition rule, we know that the space, okay, basically the Hilbert space of this two-side, basically the two-side Hilbert space is of the structure 1 tensor 1. So it's basically triplet tensor triplet. And then we can decompose this Hilbert space into the irreducible representations of the SO2 group, which becomes singlet plus triplet plus quintet. And this P2 here just means we project the, this P2 corresponds to the projector onto this spin 2 or quintet subspace within the non-dimensional Hilbert space of these two spin 1 sites. And okay, here's the proof. I'm not going into details, but basically this just a very, very simple algebra will show that the upper component is exactly the same as the one with the blue color. Okay, and now in this page, I will use the projector form of the AKLT component to show that indeed the AKLT state, which I introduced earlier, is a ground state of the component. So it is very useful to, as I said, split the spin 1 site into two spin 1 half particles, as represented by the red circles here. And we can express the spin 1 state in terms of the spin 1 half degrees of freedom. So a very useful basis for the spin 1 state in MBQC is written down here. So the three states can be chosen as the 0 energy eigenstate, elegant zero eigenvalue eigenstate of the Sx operator, Sy operator, and Sz operator, respectively. The crucial, okay, so the key thing here is that these three states are actually vowel states in the spin 1/2 basis. And now we can prove that a state like this is indeed a ground state of the AKLT component. So for simplicity, let's consider side I and side I plus 1. And the middle two spin 1/2 particles are already combined into a spin singlet. So they will contribute 0 angular momentum. And then we have the left one, IL. L means left, the IL particle and the I plus 1 R particle, the right particle on the I plus 1 side. And according to the angular momentum addition rule, these two spin 1/2 particles on the leftmost position and rightmost position can be either a singlet or a triplet, but it can never be a quintet. The angular momentum can never be 2 for these two leftmost and rightmost particles. But as I said earlier, the middle two particles form a singlet. So in total, again, the angular momentum can never reach 2. So that means the projection operator, the projector P2 vanishes for this kind of state. And since this projector P2 is semi-positive definite, this means that actually by using this state, we're able to minimize the Hamiltonian term by term. And next, I will discuss how to realize MBQC in the AKLT using the AKLT state. So this is still the conventional MBQC. We haven't gone to the SPT part yet. So I'm going to discuss two different aspects for MBQC in AKLT model. The first one is the computation. We simply teleport a single qubit rotation down the wire. And the other one will be the single qubit rotation. Let's first look at quantum wire or the quantum teleportation first. And so before that, let's look at the very standard Alice-Bob quantum teleportation. So suppose we have 3 qubits, A, B, and C. And Alice has qubits A and C, while Bob holds the qubit B. And let's also suppose that the qubit A, Alice qubit A and Bob qubit B are in an entangled state, basically a bio state. And then the task for Alice is to teleport the qubit information on qubit C to Bob. So how can Alice accomplish this task? And the answer is that Alice simply mirrors the combined system of qubits A and C in the bio basis. And after this measurement, B will be disentangled from A, and A becomes entangled with C. And so if you look at the qubit B, then the state will be exactly the same as the state initially on qubit C, but up to some Pauli operator. And this Pauli operator will depend on the measurement outcome of the combined system A and C. So as we know, there are 4 bio states in a system of 2 qubits. And correspondingly, this additional Pauli operator called bipolar operator will be identity operator or the 3 Pauli operators, depending on the measurement outcomes of the combined system A and C. Okay, so this is the basic strategy for quantum teleportation. And then we can apply this strategy to realize quantum wire in AKLT state. So what we are going to do is to measure every site just in the basis that I described earlier. The 3 eigenstates of the Sx, Sy, or Sz operators. And there's a difference from the standard quantum transportation. We don't have singlet here because we need to project all the singlet component within these two, within the physical space of the two spin-1 half particles, because we start from spin-1 particles in the APLT model. So there will only be 3 rather than 4 states on each spin-1 side. And now let's suppose Alice sits on side 1 and Bob sits on side 2. So so as you can see, the right particle, the right spin-1 half particle of Alice is entangled with the left spin-1 half particle of Bob. So this is the entangled pair. In analogy with the standard quantum transportation. And now Alice wants to teleport the information on the left. Basically, it's 1L, teleport 1L to 2L. How does she do this? She as in the protocol in the last slide, Alice simply mirrors the first side in this basis, and then the qubit 2L of Bob will be the same as the state, the private state psi on qubit 1L, but up to a Pauli operator, which is dependent on the measurement results among these 3 possibilities. And after the first round, Alice just transfer to side 2 and Bob transfer to side 3 and do it again. So in this way, we can see that information can be transported down the wire up to some byproduct operator, which is a multiplication of Pauli operators. And then having realized quantum wire, the question is how we realize single qubit rotation using PKC state. And in this case, we need to rotate the measurement basis. So basically, let's suppose that we measure all of the size in the basically in this basis, except side J. On side J, we rotate the basis a little bit. For example, so basically here I will denote the basis on side J as cat X, cat Y, and cat Z. And cat X will be a superposition of Sx is equal to Bn equal to 0 and Sy equal to 0. And you can check, it's pretty straightforward to check that again up to some Pauli operator, we can realize a single qubit rotation around Z axis by an angle theta in this way. But an important point worth to note here is that MBQC has an adaptive nature. So let's say if we really want to do rotation by an angle phi j, then the rotation angle on side j cannot be equal to phi j. We need to modify it with some possible sign factors. So this is because we need to commute this rotation operator through all of the byproduct operators which are generated before side j. And this commuting through process will generate a sign change in the definition of the rotation angle theta. So the precise relation between theta and phi j will be like this. So this page I need to explain a little bit on how do we initialize the qubit and how we perform the readout. So because although the spin-1 particles in chains are all fractionalized, we really don't have some spin-1 half particles as a separated entity. So we need to attach one spin-1 half particle on the left end of the chain and the other one on the right end of the chain. And so the n+1, so the spin-1 half at side n+1 will serve as the redox qubit. And leftmost spin 1 half particle will be used as the to initialize the qubit. So suppose qubit 0 is entangled with 1L, the qubit 1L, this one, in a singlet state. And then by performing a measurement on qubit 0, we can initialize the qubit 1L into any state that we want. Okay, so next I will move on to SPT MBQC in one chance. And this will be the main part of the talk today. So, okay, so first for a very brief summary, we can define a measurement, the notion of a measurement path. Here, these S, S0, S1, S2, and Sn, they are the measurement outcomes that we obtained in the MBQC process, actually the conventional MBQC process that I described earlier. And these angle theta are the rotation angles when we want to implement the single qubit rotations. And as I said, we need to attach a spin 1 half particle to the left end of the chain. So S0 will take the value of 0 and 1, but all of the other S will take value of X, Y, Z, because we have 3 bases in the spin 1 qubit space. And the adaptive nature of MBQC is reflected within the fact that the theta i's will in general depend on the measurement outcomes prior to site I. Okay, but a point here is that the procedure that I described earlier does not work in the SPT phase. So why it's like this? So actually recall that the SPT phase just means that we can deform the states within the SPT phase into one another by local unitary transformations, preserving the symmetry and the gap. So let's say the first line is a Characterization state. We can do a local unitary transformation preserving the symmetry to obtain a general state within SPT phase. But as you can see, due to this local unitary transformation, the fractalized particles, so this means that we no longer have the capability of manipulating the fractionalized particles side by side. So this is the reason why SPT MBQC, this is why the conventional MBQC method does not apply in a SPT phase. And this is the point that I think Austin has discussed in his talk this morning. But there's a solution to this difficulty. So basically, we can perform a real space renormalization of a general SPT state. So that means we want to consider a block of spins rather than individual spin 1 particles. And let's imagine that we block many spins together to form a single block spin. Then, because we have many concatenated sides within a block spin, some irrelevant informations will be diminished gradually when we increase the size of the block spin. And eventually, when we reach very large lengths of the block spin, only some dominant information will be retained in the block spin. And this is called, okay, so in the MPS tensor language, eventually when we reach very large length scale, we obtain fixed point MPS tensor, which recovers the form of entangled pairs. So here, these yellow circles still are spin 1 half particles, but the dashed lines actually correspond to a block spin. So there are many other degrees of freedom within a block spin, but they are diminished by the renormalization process, and we are only left with the most important ones. And as you can see, then we come back to the regime where conventional MBQC can be applied. And this kind of means that we need to consider block of size to do MBQC in SPT things. And this is discussed in a PRA paper by Robert in 2017. So the solution to this is that we need to sum over all of the measurement paths. And in some sense, this corresponds to a blocking of the size. And okay, so but in an unpublished work by Robert, there's actually a refinement of the Paris solution in the PRA paper, in the 2017 PRA paper. And this refinement has two advantages. The first advantage is that it can be applied to finite size systems, as opposed to the picture here, where we need a thermodynamically large system to implement MBQC, SPT MBQC. And the second advantage of this new work is that it defines the notions of the computational order parameter, which I will explain later. And the discovery is that this computational order parameter coincides with the conventional string order parameter in mathematical physics. And in this talk, I'm going to I will derive the computational order parameter for spin 1 SPT chains, but I will not really touch SPT. I will reformulate the AKRT chain in the summing over all paths language and obtain the computational order parameter for AKRT chain. But as you can see, the final expression is easily generalizable to non-AKRT forms, which means that it can be applied to any system within SPT base. Okay, that's the specific description. Okay, so again, we are going to proceed by in two steps. The first step is to realize quantum wire in SPT MBQC. So in quantum wire, all of the rotation angles will be taken as 0. So let's consider one particular measurement path, denoted by S1, S2, all the way to Sn. And the final state on site n+1, which is the readout qubit, will be a whole multiplication of the Pauli operators acting on the initial state psi, residing at the left position. Okay, so residing at 1L, the position 1L, where L just means left. And these Pauli operators are the biproduct operators in MBQC. And as you can easily see, okay, so this thing, all of the sigmas acting on psi is just the projection of the ground state onto the product state S1 to Sn. So this, just recall from our what we have done in MBQC. When we do measurement, it means that we need to project onto a particular basis for each spin 1 site, and that is exactly, and then we get these byproduct operators. But then, okay, but the right-hand side of the equation exactly expresses the fact that we are doing projections. And okay, and now let's do. Suppose we want to do state tomography at site n+1. For example, let's calculate the expectation value of Zn+1. And then how do we do this? Because of these byproduct operators, we need to compensate the byproduct operators by inserting its inverse of this. So this is also the adaptive. This actually originates from the adaptive nature of MBQC. So not just the measurement. Okay, the rotation angles are dependent on various measurement outcomes, but the state tomography are also dependent on various outcomes. Okay, but then as you can see, when we so these byproduct operators will generate signs when we try to commute them through Zn+1, and there will be a sign if this S, measurement outcome S, is equal to z. Oh, sorry, is not equal to z. For example, x or y, but there will be no sign if it is equal to z. So we have a sign factor here. And so that means the expression of the state homomorphy for z operator at site n plus 1 will acquire the form within this last one. And okay, so this is a graphical representation of the what I have just described. So so on each side, in addition to the projection, this cat Sj and bra Sj, we also have an additional factor, which comes from the adaptive nature of the state homomorphy at the very last readout point. And as I advocated earlier, in SPT MBQC, we need to sum over all of the all measurement outcomes. So let's do this. So basically, for every possible measurement outcome, that is to say the measurement path S1 to Sn, the probability is this projection squared. And then we need to weight we need to average the measurement outcomes according to this probability. So that is its first line. But as you can see, the probability is cancelled by the denominator in the expression of zn plus 1. And that means when we sum over, although it looks like it's pretty complicated to do the summation, but actually the result is much simplified when we do the summation. And we don't have any denominator. And on each side, we have a sum over outcomes outcome Sj times the adaptive sign times the projection. And okay, so a nice thing is that this summation, this thing here, is exactly equal to the I pi Sc. So so the final result is pretty simple. The expectation value of zn plus 1, I put a double bracket here because we do two average. The first average is within the state homomorphy. The second average is within the summation over all of the measurement paths. And this will be equal to an expectation value of some operator with expanding through the whole chain over the ground state G. And if you are familiar with the string order parameter in condensed matter physics, you can already recognize the similarity between this operator here and the string order parameter in condensed matter physics. And next, let's look at how we implement single qubit rotation SPT MBQC. So as in the okay, so similar to the procedure in dimensional MBQC, as I described earlier, we need to measure some site, let's say site K, in the rotated basis. And it can be proved that the rotated basis can be obtained from the unrotated basis by applying a rotation around z axis with an angle theta k. Okay, so a caution here is that this theta k is not equal to the rotation angle that we want to implement. We actually need to take also into account the adaptive sign, and which is shown here. And again, let's do state homomorphy. And so this time, we need to replace the bra at site K. Okay, so we need to put the rotated basis into the bra at site K. And when we do the when we sum over all of the measurement paths, as you can see here, the expression of this. Okay, so suppose we want to do state homomorphy with Pauli operator x, not z, because we do a rotation around z. So the z of Pauli will be trivial. So let's consider Pauli operator x at site n plus 1. And the single bracket expectation value is like this. It's exactly the same as the case in conventional MBQC, except that the the operator acting on side K should be rotated, basically. So that means we put theta K is equal to 0, then oh, sorry, I'm sorry. So basically what I mean, well, on the, okay, so let me correct here. So basically the expression of this single bracket expected value of xn plus 1 is exactly the same as the quantum wire, except that we need to do a rotation on side K. Okay. And again, the denominator cancels with the probability. So this is the result. Just as the case of quantum wire, we have these e to the I pi as x operators on every side, except side K, where we need to do a rotation around z axis by angle theta K. Okay, so this is a compact expression for the state homography. So okay, this needs some calculation, but I will not go into details here. But the point is that compared with the quantum wire case, we have an additional e to the I as z theta. So basically, we put theta equal to 0. This x bar 0 is just the string order parameter that appears in the expression of the quantum wire. But for single computation, we have an additional factor, not factor, I mean additional operator to the I as z theta. And okay, so basically, this expression can be further simplified. As you can see, eventually we want to take the expectation value of this thing over the ground state. But okay, so this means that it's not this operator which is important. It is really the projection of this operator onto the ground state subspace that is crucial for our purpose. So let's do that. Let's project, which is denoted by P0 here. Project the operator onto the ground state subspace. In this case, the ground state subspace is actually twofold degenerate. So remember that we have attached a P1 particle to the right end of the chain, and that will kill the twofold degeneracy on the right edge. But we still have a twofold degeneracy on the left edge. So this P0 will be the projection onto that twofold degenerate ground state subspace of the whole system. And then this e to the I pi as z theta can be written as cosine plus I sine. And then after some manipulations, the final result is this line. This line. And this line, I will not go into details, but this line in the limit of small phi k. Oh, by the way, we need to replace the angle theta k by phi k. So the actual angle we want to implement is this phi k. But theta k differs from phi k by some sign factor due to the adaptive nature of the MBQC process. So in the limit of small phi k, finally we have this result. So as you can see, what does this mean? So this means that this x bar 1, which is the operator here, is very close to x bar 0. But there are some additional terms. And as you can identify, this additional term just means a rotation of x bar 0 around z axis by a small angle. But that angle is not equal to phi k. Its phi k is scaled by a factor of expectation value of Rz. And this Rz, the expression of Rz is shown by the red line here. And what does this mean? This means that after doing all of the summation over measurement paths and do the calculations, the final conclusion is that we are not implementing a rotation with angle phi k, but a renormalized angle. So the new angle is the string order parameter Rz times the initial angle phi k. So what is okay? So this is a graphical representation of the renormalization factor RZ. This RZ is a product of many. This RZ operator is a product of many local terms, but these local terms are all identity prior to psi k. And on psi k, it is sz times e to the I plus z. And then the remaining size, the right of k, they are e to the I plus z, except the last one. The last one should be zn plus 1. And okay, so currently I only discussed the expression of state homography for poly F operator, but we can do the same for poly 1 and poly z. And the result is consistent. I mean, basically, the result is that we have a rotation, but with a renormalized angle, with the renormalization factor determined by the expectation value of the string order parameter. Okay, so as you can see, if this string order parameter is 0, that means we can never implement a rotation of the qubit. So that means whether this mu is just the expectation value of. Okay, so whether this basically whether this RZ is equal to 0 or not really determines whether we can implement SPT MBQC in the SPT phase. All right, I need to clarify one thing that I advocated earlier. So this expression, as you can see, actually applies to the whole SPT phase. Although I derived this result exactly at the equality point, but the final result is actually generalizable to arbitrary point within SPT phase. Okay, so this is the expression of this O here, this OZ here is the definition of the conventional string order parameter in mathematics within the Howland phase of the string 1 chain. And it's pretty straightforward to see that this O operator coincides with the string order, the computational order parameter is RZ by carefully identifying the size. So we need to identify I with k, but we need to put j to be n plus 1. Okay, so so the result here is not just generalizable to arbitrary points within the SPT phase. As you can see, if we make these spin operators S within the expression of RZ to be some arbitrary integer spin, this set of equations still hold. So this means that all of the pairs of the results can actually also be generalized to arbitrary integer spins. And actually, that could be a formal algebraic proof for such generalization, which will be discussed in Robert's unpublished work. But I'm not going to go into details of that. Okay, so this is here is a summary of my talk today. The first, MBQC and SPT MBQC are discussed for one chain. And the second point is that the computational order parameter is obtained for integer spin chains, which can be used to characterize the computational power. And finally, the computational order parameter coincides with string order parameter. So finally, I would like to acknowledge Robert and also Anna, who is a student of Robert. Thank you for watching.
So, are there any questions?
I have two questions. So my first question is, when you do this doubling up of the expectation value, essentially summing up over all paths, it would naively appear to me that that would be like terribly inefficient if that's how the computation is actually implemented. So is this just something we do for the purpose of the calculation, and this gives us a very nice theoretical result, to be sure, or is an actual SPT MBQC procedure going to be quite inefficient due to this?
Okay, so actually this question has already been explained by Robert in a group meeting before. So although we need to do a summation for all of the random outcomes, but in practice, let's say we want to do simulation of this method on a real computer. We really don't need to solve all of the outcomes. Then we already got a pretty high precision. So for example, I imagine that the probability distribution will be concentrated around some point within the space of all possible outcomes, and just selecting enough points within those the complicated regions will be enough. So actually another understanding of this is to think of the analogy with Picabo. So in Picabo, we want to simulate the possibility in Picabo to really simulate the probability distribution of a function, which is actually parabolic even at the max. That will have a manually state. But in practice, we don't need to improve simulation. We don't need to solve all of the possible paths within one problem. We already have a pretty nice result.
My second question is, what part of this derivation would fail when you use the state that isn't in the SPT phase? So what is the point where that would come in general?
Okay, so this potential value of string order parameter or string order parameter R Z. Okay. So and then as you can see, we have no rotation implement.
Thank you.
Yeah, so is the expectation value of this framework parameter 1 the AKL equal? Or
okay, so I derive this so this is the derivation that we can one. But actually we want to apply this set of formula to general quantity in the condensed. And in that case, expectation value will be taken with respect to the quantity, the particular the quantity of the particular point in the condensed.
Steve, next question. David, you want to go ahead?
Hi, thanks for the talk. I was wondering, you said, so all these calculations were for the AKLT point, right? You said?
Yeah.
And you said, but you said you can do the calculations away from the AKLT point. To do that, do you use MPS explicitly, or how do you do the calculation away from the AKLT point?
There could be a form of algebraic manipulation away from the AKLT date, but I didn't start that here.
Sorry, I'm having a slightly hard time understanding. Have you changed the microphone you're using? I can't quite hear because I think now it's going to Michael's microphone, not yours.
David, that's already analyzed the system.
You can unmute yourself. Yeah, unmute yourself on your computer then. You're muted right now. Can you unmute yourself?
I think they are so can you hear me now?
I can.
Okay, so regarding your question, so away from the AKLT point, there could be a formal algebraic manipulation we can now discuss in this talk. And the basic idea is to study some equation of motion for the logical cubic operators. So I mean, basically, The derivation can be made rigorous even away from data.
I see, and that calculation doesn't use the MPS.
MPS is not involved.
Okay, thank you.
Yeah, I have like, what about? I can foresee that it can be extended to different speeds, but I wondered why you said only integer speeds. Like, what fails if you have like 3/2 speed, for example?
Okay, so the simple so the straightforward answer to this is that there's no SPT phase in half integer speeds. Yeah.
Okay.
So that's not that cannot be very easily seen from the derivation. But I mean, the short answer is that the SPT phase only applies to integers.
Yeah, and there were also this like mentions earlier about twisted string order parameters or multi-scale string order parameters, but they're not needed here, right?
Yeah, so they are not. Yeah, they don't appear.
Yeah, thanks. Does anybody else have a question? Then I think if that's not the case, I think